everyone! Today we're going to unravel a huge mystery, one that connects something as simple as dropping your keys to, well, the grand dance of the planets. We're diving deep into the universal rules of motion, all thanks to that invisible force we call gravity. So it really all boils down to this one question. I mean, think about it. An apple falling from a tree and the moon circling the Earth. They seem like they couldn't be more different, right? One just plummets straight down. Bam, hits the ground. The other just keeps on going, endlessly. But what if I told you they're basically the exact same thing? Yes, seriously. Okay, so first things first. Before we get to the wild stuff, let's get a handle on the force we're all feeling right now. That constant, familiar tug pulling us down towards the center of the Earth. You know, a lot of people think of gravity as just an Earth thing, but it's not. It's literally a universal rule for anything that has, well, stuff, mass. Any object with mass pulls on every other object with mass. So yeah, that coffee cup on your desk, it's technically pulling on you right now. The reason you don't go flying towards it is just that the Earth is, well, she's a whole lot bigger, and her pull just completely overwhelms everything else. Now, this is a really, really important point. Gravity doesn't just pull something down at a nice, steady speed. Nope. It's constantly yanking on it, making it go faster and faster and faster the longer it falls. That's what scientists call acceleration. And here on Earth, that acceleration has a specific number attached to it. It's 9.8 meters per second squared. Now, what's so wild about this number is that it applies to everything near the Earth's surface. A feather, a bowling ball, doesn't matter. If you could get rid of air resistance, they'd accelerate at the exact same rate. So what does that number actually mean? It's simple. For every single second something is falling, it picks up another 9.8 meters per second of speed. Okay, let's put that into perspective. Imagine you drop a rock. At the very start, its speed is 0. After just 1 second, boom, it's already moving at 9.8 meters per second. Wait another second, and it's doubled to 19.6. By the third second, it's going 29.4 meters per second. See the pattern? It's just a constant, predictable buildup of speed, all thanks to our friend gravity. All right, so falling straight down, check. We've got that covered. But this is where things get really cool. What happens when you don't just drop something, but you throw it sideways? Okay, time for a classic brain teaser. Picture this. You're standing on top of a cliff. You've got two identical cannonballs. With one hand, you just let one drop straight down. With the other hand, at the exact same instant, you fire the second one straight out, horizontally. The question is, which one hits the ground first? Come on, what does your gut tell you? Probably the one you dropped, right? It has a shorter path. Well, prepare to have your mind blown. The answer is, they hit the ground at the exact same time. I know it sounds totally wrong, but it's true, and it shows us something absolutely crucial about how gravity works. It only cares about the up and down motion. That sideways push you gave the second ball, gravity couldn't care less about it. It has zero effect on how fast that ball is falling. So here's the secret. The key is to think of the motion in two separate, completely independent parts. It's like they're in different dimensions. You've got the horizontal motion, the sideways part. With nothing to slow it down, it just cruises along at a steady speed. Then you have the vertical motion, the falling part. And in that dimension, it's a completely different story. It's acting just like the ball we dropped. It's in pure free fall, picking up speed downwards at that same old 9.8 meters per second squared. And this idea, the simple idea of splitting motion into two parts, is the master key that unlocks the entire universe, seriously. It's what led Isaac Newton to one of the most incredible what-if scenarios. A thought experiment that connects a simple cannonball to the orbit of the moon. Okay, check this out. Newton imagined a cannon on top of a mountain so tall it pokes out of the atmosphere. So, step 1, you fire the cannon with a little bit of gunpowder. The ball goes a short way and thud, it hits the ground. Okay, step 2, add more gunpowder, fire it faster. It travels much farther before it lands. Simple enough. But now, what if you fire it really, really fast? Something incredible starts to happen. The cannonball is still falling, but it's going so fast horizontally that the Earth literally starts to curve away underneath it. And if you can hit one perfect magical speed, the cannonball is still falling, but it's falling around the Earth. It never gets any closer. My friends, that is an orbit. And that, right there, is the secret sauce. An orbit is just a perfect balancing act. It's a tug of war between your forward speed, which wants to fling you out into space, and gravity, which wants to pull you straight down. The trick is to go sideways so incredibly fast that you're constantly falling toward the Earth, but you just keep missing it. So, what is that magic speed to orbit just above the Earth's surface? Get this, it's about 8 kilometers per second. That's almost 18,000 miles an hour. To put that in perspective, that's like traveling from New York to Los Angeles in about 8 minutes. It's just mind-bogglingly fast. Okay, so here's one half of the equation. Because the Earth is a giant sphere, for every 8 kilometers you travel in a straight line forward, the ground will curve away from you by about 5 meters. And now for the other half. Remember our falling objects? In 1 second of free fall, how far does something drop? Yep, about 5 meters. Do you see it? The numbers match perfectly. If you can travel 8 kilometers sideways in 1 second, you will also fall 5 meters down in that same second. Your fall perfectly matches the curve of the Earth. You are literally falling around the planet. And here's the most amazing part. This isn't just a clever thought experiment with a cannonball. This one beautiful, simple rule, it's what runs the whole show. It's the blueprint for our entire solar system. So if you remember one thing from all this, let it be this. Being in orbit does not mean you've escaped gravity. Not even close. The International Space Station, the Moon, every satellite up there, they're all being gripped by Earth's gravity. In fact, gravity is the very thing keeping them in orbit. They are all, every one of them, in a constant state of falling. And this same dance is happening all over the cosmos, just on bigger and bigger stages. Our satellites, they're falling around the Earth. The Moon, it's doing the very same thing, just from much farther out. And what about us, right now on planet Earth? We are in a constant state of falling around the sun. It's the same principle, over and over again. It really is just this beautiful cosmic dance, isn't it? A perfect balance between moving forward and falling down, playing out on every scale imaginable. Everything in orbit is locked in this state of forever falling, but always moving just fast enough to perpetually miss. So let's go all the way back to our original question. What do a falling apple and the orbiting moon have in common? The answer is everything. They are both just objects in free fall, pulled by gravity. The only difference is that the moon has a massive amount of sideways speed that the apple doesn't. That's what lets it keep missing the Earth. It's one single, elegant rule, governing everything from an orchard on Earth to the farthest reaches of space. And that brings us to one last little puzzle to chew on. We now know that astronauts on the space station are constantly falling. The station is falling, they're falling, everything is falling together. So, why do they look like they're floating? Why do they feel weightless? Well, that sounds like a great question for another day. Thanks for joining me.